All right, Calc 3, welcome on in. It's Tuesday, November 2nd, and it's the start of week 12, right? And it is exam week. We have an exam open. Chapter 13 exam, right, is out there, ready to go. Oh, yeah, chapter 13. So, yeah, hopefully you're getting on that and preparing for it. It'll be due, of course, on Sunday night. I believe that's the 7th of November. Yeah, hard to believe it's November already, but there it is. So let's get started though with other new material. This is not, of course, on your exam, but not this exam anyway. But we did start chapter 14 last video, and so I'm still in 14.1. I'll probably get through 14.2 today, depending. They're very connected, the two chapters sections or so. We'll probably do some overlap on both of them today as well. So to get us started, let's remember what we were doing last time. So I thought I found yes, right there. Talking about an iterated integral. Right? So let's remind ourselves what that means. An iterated integral means an integral of an integral, right? And so something like this maybe, integral from 0 to 2 of the integral from 0 to 6x squared of the function x cubed with respect to y first, then with respect to x, right? And so you read these from the inside out, right? So we'll dispense with all the parentheses we did last time, and we'll just sort of push it all together like this. But I do want to bring your attention to this, right? This is the first integral that you're doing. You're going to integrate x cubed with respect to y from 0 to 6x squared. Now remember, these are y values, right? This is y equals 0 to y equals 6x squared. And so relative to y, 6x squared is a constant. So this is totally legal, right? Because I'm integrating from a constant to a constant relative to y. So this is totally cool and good to go. So here's what I'll do. You basically treat these as parentheses for now, the integral from 0 to 2 and dx. Treat those as parentheses right now. And then go ahead and integrate this. This is going to be x cubed. That's a constant for now. And times y, evaluated from 0 to 6x squared. Right? And so then you go ahead and plug in for y these values. So I'm going to get x cubed times 6x squared minus x cubed times 0, then dx. And by the time you get to this step, you should only have variables of the variable remaining, right? This should be all x stuff here. No more y's should be present by the time I get to here. All right, now I can simplify a little bit. This is going to be the integral from 0 to 2 of 6x squared times x cubed, which is 6x to the 5th, and then minus nothing. And so now I'm just left with this integral. This is going to be what? Raise the power by 1, divide by new power, and the 6's will cancel. Evaluated from 0 to 2. And so I end up getting 2 to the 6th minus 0 to the 6th. And 2 to the 6 is 4 times 4, 16 times 2, 32, right? Is that right? 4 times 4. No, it's not right. 14 times 4, 64. There we go. Leave it to me to screw up the arithmetic at the end. Get through the calculus just fine, but then the arithmetic at the end gets me. Okay, is everyone okay with that procedure, right? Because right now it's just basically procedure and how does one do this problem like that, right? We'll talk about what that number means, what we can measure with it, what it does in the next coming classes, right? But for now, all I'm asking is, are we okay with this just calculation? Yeah? Because I want to now get into a little bit more about these limits of integration and how they're functions. And you see how the domain of integration is two-dimensional? There's like y values going on, like y is going from 0 to 6x squared, but then x is going from 0 to 2, right? So when x starts at 0, for instance, do you see that the y is only going from 0 to 0 in that one instance? Yeah. And if x was 1, which was halfway in between the interval from 0 to 2, if x was 1, then this integral would only be going from 0 to 6, right? Because x is currently 1, yeah? And then if x was 2, all the way at the end of its interval, notice that this integral goes from 0 to 6 times 4, 24, right? So this integral goes from 0 to 24, right? So it's almost like the x values are doing a thing going from 0 to 2, but as the x values go from 0 to 2, y is doing from 0 to 6x squared, right? So now think about that. 6x squared is actually a parabola, right? And so this is y equals 6x squared. This, of course, this line is y equals 0, right? And this is x equals 2 and x equals 0. So in effect, what I'm doing here is starting at the x value and going vertically from 0 up to the curve. At another x value, I go from down here up to the curve, from down here up to the curve, from down here up to the curve. For various x values, I'm always sort of going from bottom to up. Do you see that? And this is literally how I'm traveling, quote unquote, through the integral. You didn't have to think much about this in Calc 1, right? So like, for instance, if I said, okay, I want to integrate the from 0 to 3 of x squared dx, right? What you didn't really have to visualize, because it wasn't really, well, needed, right, is that you're starting at an x value of 0, and you're sort of sweeping x through all values until you get to 3, right? That's what you're really doing in an integral. If you remember that Riemann sum stuff where the you would build boxes and like cut this into pieces, right? And you'd get like representatives from each one, and then you'd have to make the boxes thinner and thinner and thinner and thinner, right? The result of that is thinking that x travels, if you will, through all values between 0 to 3, right? And it wasn't much to think about in Calc 1. That's all it did, right? It's basically for every x value, you would plug it in to find the height of your rectangle, and then take that sum and then take the limit of that. All of that's happening in the background when you perform the fundamental theorem of calculus, right? So you sort of forget that that's where this comes from. But in essence, you are traveling through every point in the domain, 0 to 3. Now here, you're also traveling through every point of the domain, except now that domain is two-dimensional, right? And so there's a couple different ways to go through every point in this domain, right? So if I'm integrating from 0 to 2 of the integral from 0 to 6x squared of a function f of xy dy dx, I really am going from y equals 0 to y equals 6x squared, right? Which is a parabola. And then x goes from 0 to 2, right? And so 0 to 2 would be maybe like, here's 1, there's 2, like that. And I literally am thinking about, how do I traverse every point in this two-dimensional space? And you see this dy dx suggests that I'm doing vertical lines at all x values. So at this x value, what do? I go from 0 to the curve. So at this x value, I sweep through this way. Then at the very next x value, sweep through, and I start at 0, don't I? And you see, as I keep doing this, it fills in the entire space. It's almost like contacting every point in that two-dimensional domain. Just like we contacted every point on this interval, we're going through every point in this two-dimensional space. Okay? Does that make some sense, right? That's sort of going through every point in that domain. Now, the fun part of this is, there's like two ways to do this, isn't it? Right? I could write vertical like this, vertical lines or arrows, I might say, vertical arrows that sort of go from bottom to up, and then you move over to the next x value, bottom up, bottom up, bottom up. Or you could conceivably sweep through this way. You could say, okay, same shape, but instead of vertical arrows, maybe I sweep through starting on the bottom and go horizontal arrows from left to right. Then change height, left to right, change height, left to right, change height, left to right, change height, left to right. And you see that that I could also visit every point in this domain that way. So there seems to be two different ways to traverse the two-dimensional domain. I could do like vertical lines and then push those vertical lines horizontally, or I could use horizontal lines and push those lines up vertically. See that? There seems to be two choices. We're going to find that those two choices are dictated by the order of dy dx or dx dy. The order that's given there tells you which way it's being drawn out. Dy dx is this way. Dy dx takes vertical arrows and then pushes them through all x values that you're sweeping through. Okay. Let me do another one where we can sort of think about what the domain of integration is for this. So now I'm taking a break from calculating the whole integral and just looking at the domain part right now, the limits of integration. Right? So if I had something like this, integral from 0 to 1 of the integral from, let's say from 0 to x of a function, dy dx. We can actually glean quite a bit of information about the domain of integration here. What is being, quote unquote, integrated over, right? Well, I could draw a picture just like this. So this is going from y equals 0 to y equals x. Y equals 0 is this horizontal line down here. Y equals x is the diagonal line, like this. Right? And what this is suggesting is I'm always starting my vertical arrow from the bottom curve, which is y equals 0, and I'm going up until I hit the top curve, which is y equals x. See that? So I'm going from here to there. Now, how far am I going from bottom up, bottom up, bottom up? How far over do I go? Well, x is only between 0 and 1. So I start the arrows here at 0, and I keep doing these arrows until I hit 1. That's going to be my last quote-unquote arrow right there. So do you see that how that's going to now be able to traverse every point in here, and it's going to fill in this bottom triangle? That's what we call the region of integration. How are we doing with that? Does that make sense? Okay. So in some sense, you're actually plugging in like every point along the way. We don't have to do it that way, but behind the scenes, what's going on is literally I'm plugging in all of these values into something, and the math is going to add it all up and take that Riemann sum idea and bring it all together. Thankfully, we have a fundamental theorem of calculus, so we don't have to think of it that way all the time. But that is, in essence, what we're doing. Excuse me. Let me try another picture here. Let's do the integral from 1 to 4 of the integral from 1 to square root of x of a function. And we'll do dy dx, and then we'll do dx dy examples. Go ahead and see if you can draw out the picture even before I do. All right, so here's the picture. Here's the xy plane. This is the x-axis, this is the y-axis, right? And we're going up from y equals 1 to y equals square root of x. Okay, so let's go ahead and put the line y equals 1. That's going to be the horizontal line here. So this is the horizontal line y equals 1. That's where all my up arrows start. And then they end at y equals square root of x. So if I graph y equals square root of x, that's going to be the top curve, isn't it? So let's go ahead and graph that. I know that the square root of 0 is 0, so the square root goes through that point. The square root of 1 is 1, so that's actually going to be here. And then square root of 2 is not nice, square root of 3 is not nice, square root of 4 is 2. So that does that. So, oops, it missed. Let's fudge that point a little bit. There we go. Missed. All right, but does everyone see that this is y equals square root of x? Yeah? So now let's sort of shade the region that I'm going with. Y is always starting at y equals 1, this horizontal line, and going up until it hits the square root of x. And what x values am I doing this for? I'm starting at the x value of 1, where there's not much to travel because these two curves are on the same point. But I'm doing this all the way to 4. 2, 3, 4. So that means it's filling in this right here. Going from bottom up, bottom up, bottom up, bottom up, bottom up, all the way until I get to x equals 4. This is the region of integration. Okay, how are we doing with that? Does that make sense? Let me know if that makes sense or if you have questions in the chat. Okay, good. All right. Now I'll switch it on you. dx dy is horizontal, so it's going from left to right. So the arrows are going from left to right, but the idea is very similar. So suppose I have now the integral, the iterated integral that does this. I want to integrate from 0 to 1 of the integral from 0 to y of a function, but I want to do dx dy this time. Okay. So the rules are basically the same here. Notice that x now is going from x equals 0 to x equals y, right? So when I go to graph that, realize now that x equals 0 is a vertical line, isn't it? This is x equals 0 right here, right? And x equals y is the diagonal line, right? This is x equals y or y equals x, right? But please note that I'm going from left to right. So this is my left curve, and I'm going over, sweeping over until I hit the right curve. From left to right, from left to right. Now, what heights am I doing that from? I'm starting at a height of 0, which is down here at the origin. So go left, right, left, right, left, right, left, right, left, right, all the way up to y equals 1, which is up to here. And so that's going to be this triangle here. So that's the region of integration for that iterated integral there. We're not necessarily used to x equals graphs, right? But yeah, we have to start to get used to them a little bit here. Let's try one more of these, and then we'll move on and see what the general situation is like. We'll integrate from 0 to 2 of the integral from 0 to the square root of 4 minus y squared. Oh gosh, how rude. And then this is dx dy. Okay. So again, I want to just draw the picture here. So this is starting at dx x equals 0, which again is this vertical line. So x equals 0. And then it goes to the right until it hits x equals square root of 4 minus y squared. Now that you might not understand right away what shape that is, but if you do square both sides, you get x squared equals 4 minus y squared. And if you add y squared, you get the form of a circle. Look at that. But since x is the positive square root, this curve is only the semicircle, isn't it? On the positive side of x, right? So what I got going on here is this curve, x equals square root of 4 minus y, is this semicircle, right? Now, this should go down here, but I know that y starts at 0 and goes to 2, so I know this doesn't extend past here, because here's y equals 0, right? So I can just stop drawing my graph right here. But if this was like -2 to 2, then this would continue on, and I would be integrating from -2 to 2, and I would have arrows filling in all of the semicircle, right? But here, since I go from left to right, at what heights? Only the heights from 0 to 2. So it starts down here at 0 height, goes to 1 height, and then goes to 2 height. And so this does fill in this entire quarter circle, doesn't it? Maybe that's a semicircle? Okay. So the limits of integration communicate a geometry to you, don't they? There's a certain geometry that we can. I didn't tell you anything about the surface. I didn't tell you anything about the function that we're integrating over. This is the domain itself. We didn't have this issue in Calc 1 because our domains were all one-dimensional, just an interval from this to this. So we didn't have to think about it too hard, right? Here, we have geometry happening in the domain of integration itself, let alone the surface, what's going on in this function, the graph of that surface. So you can see with these sorts of iterated integrals, it seems like we might have two pictures at a time going. We'll have like the domain of integration, that's like the top view, and then we'll care about maybe the picture of the surface, right? And like I said, in Calc 1, we didn't have to worry about the picture of the domain because it was always a boring just interval. That was it. Okay, so in general, this is what happens. In general, we can have something that looks like this. Let's see. In fact, yeah, let me now I'll join in on the book and talk a little bit about what it's doing. Right? Now, we're going to take a slight detour here and talk about finding area of a plane region. Okay. Now, this is something you already know how to do from Calc 1, right? And early on Calc 2. You found areas under the curve, right? That was something you've done before. But now I want to show you that I can do area with an iterated integral idea as well. I'm not suggesting that you actually calculate area practically this way, but I'm showing you that iterated integrals connect with the idea of area. And soon enough, they're going to connect also to volume under the surface. Ooh, that is the next step up, right? I mean, in Calc 1, you found areas under the curve. The next step up would be finding volumes under a surface, wouldn't it? And so we're working our way there, okay? So picture time. Let's talk a little bit in general here. So suppose I have a function, let's call this g1. So this is y equals g1. And let's say I have another function up here, like this, and this is y equals g2. And I know that g1 is less than or equal to g2. Right, so g1 is always bottom curve, and g2 is always the top curve here. Okay? And let's say that I only care about this from some x value from a to b. So really, that gets me a region that looks like this. And I might ask, what is the area of this strange shape? Right? What is the area of that strange shape? Kind of looks like a COVID mask, doesn't it? Oh, even in math, you can't get away from it. Yikes. Okay. Anyway, pretend I didn't say that. Now, in Calc 2, you did learn an area formula for this. I think this is like the very first lesson in Calc 2, like the first day or night of Calc 2. You learned the following, that the area of this could be thought of as a single integral. This can be thought of as the integral from a to b of the difference of the two functions. So top curve minus the bottom curve with respect to x, right? That's from Calc 2. Okay? And not new, by the way, right? That's not new. Okay. But now, using our multivariable perspective, I can actually write this difference of two functions in an interesting way. consider the following. What would be the integral from g1 of x to g2 of x with respect to y? Right, with respect to y. Well, this would be like integrating 1, right? And this is totally cool to have an integral with respect to y. These are constants relative to y, right? They are functions of x, but they're constants relative to y. And so I integrate the 1 and I get y evaluated from g1 to g2, right? And by the fundamental theorem, that's going to get me g2 of x minus g1 of x, isn't it? That's just the difference between the two functions. But that's exactly what this is. So I do have an iterated integral way of looking at area, don't I? What I can think of now, so therefore area could be thought of as the integral from a to b of the integral from g1 of x to g2 of x with respect to y, and then that integral with respect to x. And so if you were to calculate this iterated integral, you would find the area of the corresponding domain of integration. And so that is a way of looking at that area, right? So that's literally finding the area of the domain of integration, just doing that, right? I want to point out, notice that the surface that we're integrating over here, this function, f of xy equals the constant 1 in this context. Right? In this context, that surface that we're integrating over is 1. Okay? Right, and what that numerically tells us is the area of this region. Okay, awesome. So let's see what we can do with this. Right. Again, this is not too earth-shattering because we had a single integral way of looking at this in Calc 2. So you might be thinking right now, like, why do I need an iterated integral view of this? Remember, this is working our way up to something bigger, right? So this is not the only thing that iterated integrals do, but it is a stop along the way of getting something bigger here, right? So here's a problem just to practice this idea. Let's find the area between, find area of region bounded by sine of x and cosine of x between x equals pi over 4 and x equals 5 pi over 4. Okay. Now, first things first here, I do need to get a sense of what the top curve is and what the bottom curve is, right? Top curve, bottom curve. So is sine greater than cosine, or is it the other way on this interval? I mean, obviously the easiest way to answer that is just to look at a graph, right? So let's go ahead and bring up GeoGebra here. And I will go ahead and graph sine of x. And let's graph cosine of x. And then x equals pi over 4, that vertical line, to x equals 5 pi over 4. Ah, okay. Well, there we have it. This is the region that I want to find the area of. In fact, I think there's a formula, there's a way I can do this. Yeah. Let's do integral between, that's a command, integral between f comma g comma pi over 4 comma 5 pi over 4. I think that does it. Yeah, nice. So GeoGebra just shaded in the region that I'm trying to calculate here, right? But if I want to do this on paper, the bottom line is it's sine that's on the top curve, and it's cosine that's the bottom curve, yeah? So let's set up an iterated integral that does this, that calculates this number. By the way, GeoGebra found it pretty quickly and got an answer of 2.83. Let's see if we can find that integral, the answer, the area of 2.83. All right, so the area should then be the integral from an x value to an x value, which would be pi over 4 to 5 pi over 4, of the integral from bottom curve to top curve. Bottom curve is cosine, top curve is sine, of dy dx. Right? That would be the setup for an iterated integral version of this area. Yeah? Now, calculating this is going to be just like a Calc 1 problem or Calc 2 problem, because in an area context, this is always going to be a 1. So that first integration is always going to be trivial. It's going to be like y from cosine to sine, which is literally just the difference of those two functions. And that's what we get with Calc 1's formula, or the beginning of Calc 2, right? We would start out saying, oh, just take top curve minus bottom curve and integrate that. That would get you the area in between. See what I mean? So thinking of it this way doesn't add in any, quickness here, right? It's actually one more layer that we don't really need, practically speaking. But I want to show you that there's the connection there. Okay, now to integrate this, let's just do this carefully here. The integral of sine is negative cosine. The integral of negative cosine is negative sine. And I'm evaluating that from pi over 4 to 5 pi over 4. So that means I'm going to get negative cosine 5 pi over 4 minus sine of 5 pi over 4 minus a minus cosine pi over 4 minus a minus sine of pi over 4. So let's see, pi over 4, sine and cosine of pi over 4 is both root 2 over 2. So this is going to be root 2 over 2 plus root 2 over 2. 5 pi over 4, that's going to be in the third quadrant, right? 5 pi over 4. And so sine of that is going to be root 2 over 2, but negative, right? So that's going to be minus a minus. So that's plus root 2 over 2. And then cosine of 5 pi over 4, again, that's in the third quadrant. That's going to end up being a negative root 2 over 2, but there's a negative in front. So I get root 2 over 2. So it looks like I get 4 of those. So it looks like my area should be 2 root 2. And does that happen to be 2.83? 2 times root 2? It sure is. Look at that. 2.83. So GeoGebra, I confirm with GeoGebra that it found the area correctly. Okay. Awesome. So iterated integrals can be thought of as finding the area of certain regions of integration here, yeah? Let's see. Okay. All right, let's stick with this theme for maybe 1 or 2 more examples. Let's see what we make of this. I want to perform the integral of, from 0 to 2, of the integral from y squared to 4 dx dy. Okay. I'd like to calculate this iterated integral. Now, the first suggestion I have for you is please draw the domain of the integration. Draw the domain, what we're working with. I think that's going to be a super important thing to visualize. Right? It might not be important to visualize the actual function that we're integrating over, which is 1. By the way, that's just a horizontal plane, isn't it? At z equals 1. So it's just a horizontal plane that's the surface that I'm integrating over, if you will. But I do want to see the domain of integration, especially in this example, because we know, because I'm integrating over 1 here, that this is going to represent the area of the domain of integration. So I want to actually see what I'm taking the area of. Okay. dx is first. That means left to right arrows, right? And so, yeah, maybe you should write that somewhere. Dx, dy is left to right arrows. Dy, dx is vertical arrows. Okay. All right. So I'm going from x equals y squared on the left, and I'm going to x equals 4 on the right. Okay, well, x equals 4 is definitely a vertical line. So let's get that on there. So here's x equals 4. X equals y squared. Okay. Isn't that the same graph as y equals plus or minus the square root of x? Right? Solving for y. So in other words, this is a square root function, which we graphed earlier. So this is the height of 2. Here's the height of 1. Yeah. So we have a little picture here, and we're going from left to right, right? And the heights, though, the arrows are horizontal. And what levels are we pushing those arrows through? We're going from a height of 0, which forms the bottom of this shape, up to 2, which forms the very top of the shape. So this is going to fill in left to right every dot in this shape. And once I calculate this iterated integral, I'm going to have the area of this shape. Okay? Everyone with me there? We're doing all right with that? So I'm going to go ahead and do that. I'm going to go ahead and do that integral. So area here is going to equal 0, integral from 0 to 2, of integral of 1 with respect to x is x, evaluated from y squared to 4. Plug in the 4 for x, minus plug in the y squared for x. So now I'm calculating this integral. So this integral is going to be 4y minus y cubed over 3 from 0 to 2. And that's going to give me a quantity of, put a 2 there, that's going to be 8, minus 2 cubed is 8 divided by 3, so 8/3, minus 0, minus a minus 0. So I get 8 minus 8/3. Let's see here. 8 is 24/3. 24 minus 8 is 16. Looks like I get 16/3 as the result. Okay. Not bad. That's the area of this shape. Okay. But now, there's more than one way to look at this, right? This is a dx dy integral. Is there a way to calculate the same thing, but then using vertical arrows instead? Right? Now, theoretically, just thinking about that, that should be totally the case. That should be, I should be able to just go dy dx instead and then get the same quantity, right? Because it shouldn't matter if I draw it out this way, the shape, or if I draw it out this way. It's the same amount of area either way, isn't it? So let's take a look at switching the order. This is going to be an important thing to do in our future as well. Switching the order of integration. Now, for this example, there's not really a good reason to do that, although it's going to be instructional, right? Basically, that's our good reason, is that it's instructional, right? Trying to get this to stay flat, but it is not liking that. Let's try that. That's better. Okay. So, switching the order of integration. Literally what I want to do is write integral from something to something of the integral from something to something of dy dx instead. Instead of dx dy, I want to do dy dx. Now let's see if we can do this. Let's think this through. Switching to dy dx means I have vertical arrows. So I have to start to think about what is the bottom curve that I'm starting these arrows at, and what is the top curve that the arrows end at. Do you see that the bottom curve is this horizontal line? That's y equals 0. So this thing should start at y equals 0. The arrows start at y equals 0, this wherever I'm at, it starts here, and ends when it hits the graph of this function. And what is this function in terms of y equals? Well, that's y equals square root of x. See that? And then where do I run these arrows from? The vertical arrows start at 0, and they go until 1, 2, 3, 4. The integral from 0 to 4. There I've just switched the order. Do you see how you have to look at the geometry and sort of piece it together that way when you switch the order? Now I promise you that this will be the same quantity as this, right? I ended up getting 16/3 here. I guarantee you I'm going to get 16/3 here as well. So let's go ahead and do that for practice and for confirmation that we're going to actually get the same thing. Okay, so let's try this. Integrating this from 0 to 4 of y, evaluated from 0 to root x. All right, that's going to get me the integral from 0 to 4 of the square root of x dx. Then I integrate that. That's going to be square root of x, which is x to the 3/2. Divide by 3/2, or multiply by 2/3. Evaluated from 0 to 4. Okay. So what happens here? I'm going to get 2/3 times 4 raised to the 3/2 minus 0. Is that the same thing? Yeah, the square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. I get 16/3. These are the same. Okay? So switching order appropriately should get you the same value. Now you can see that this might be nice because maybe one direction is really terrible and tough, and maybe the other direction isn't so bad. You know I got an example like that coming up soon, right? Right? Where all of a sudden, switching the order becomes quite important. Not only just nice to do, but like it's impossible to do otherwise maybe, right? And so that could be an issue here. Let's see. Do they have an example like that? Yes. Yes, they do. All right, let's try one like that. Okay, let me load something up real quick too while I'm here. Okay. All right, awesome. Let's try this now. So let's try to integrate the integral from 0 to 1 of the integral from y to 1 of sine of x squared dx dy. Okay. Now this seems innocent enough at first, but if I stick with the sine of x squared, by the way, here, right, I have to integrate this with respect to x. And so what is the integral of sine of x squared? I mean, I certainly know the integral of sine, right? I mean, the integral of sine of x dx, that's simply negative cosine of x, right? No issues there, right? But the integral of sine of x squared is not negative cosine of x squared, right? Because, for instance, if I took the derivative of negative cosine of x squared, I would say that I would have negative times the derivative of cosine, which is negative sine, so that would give me positive sine of x squared, but then I have to multiply by the derivative of the inside, so I get this extra 2x that wasn't there. So the derivative of this is not that. So this is not true, right? And coming to find out, not only do you not know the integral, the antiderivative of sine of x squared, there doesn't exist a closed form for the integral of sine of x squared. Let's see what Wolfram Alpha has to say about this. All right. So if I ask Wolfram Alpha, hey, what's the integral of sine of x squared dx? Okay, it's thinking about it. You can hear my dog. My dog is upset about it. It's like, how dare you integrate the sine of x squared? And you get an answer. Oh, cute. Look, I got an answer. Square root of pi over 2 s of square root of 2 over pi times x. What? Plus constant? What the heck is s of? Oh, over here. S of x is the Fresnel S integral. Okay. That now I'm more confused. So click on that. And let's see. What the heck is that? Oh, yeah, definition. Okay. What is the S of x Fresnel integral? Hmm. I think I've lost the plot here. I don't think this is anything that's going to be useful for us. This is not our understanding of this, is there? Right? And so look at this. By the way, remember how I said it was S of? Well, look what S is defined to be. S is literally defined to be the integral from 0 to u of sine of x squared. So it's circular. It's circular. It's literally saying that the integral of sine of x squared is the integral of sine of x squared. It didn't actually do it, right? It didn't actually calculate what that function is. And the reason is that there isn't a closed form function that exists. Now, that doesn't mean you can't work with it and that people don't work with it and try to say all sorts of things about it, like graphing what this should look like in the complex world, right? In the complex plane and all that good stuff, right? But the bottom line for you and me right now, there is no antiderivative in closed form that I can use for this integral. So I'm stuck. I'm stuck. If you make me integrate this with respect to x first, I'm stuck. Right? What to do? Well, if you're stuck with a dx dy, let's try the other way, right? Since integral of sine of x squared dx is does not have a closed form antiderivative. When I say that, by the way, closed form, it just means that numerically I can get at it. So it's not saying that it doesn't have an antiderivative. There is, this is integrable. You can take the integral of this function with respect to x. What you can't do is use the fundamental theorem to do that. Right? You have to maybe use trapezoidal rule or Simpson's rule or some other numerical approach to integration to get a quantity for this. So this is totally integrable, but I can't use the fundamental theorem because I can't get an antiderivative in a closed form. So that's what I mean when I say that. Okay, now, so let's switch. It was integrating against x that was the trouble here. Maybe I should integrate with respect to y. Because now, at least that way, I get to think of this as a constant for the time being. And let's see if anything works out. So, need to switch order. By the way, this does not guarantee anything's going to work, but it's, this is impossible this way. So might as well switch and see how that is, if that's impossible or if that's okay. So I'm going to say integral of the integral of sine of x squared, but this time I hope to write it as dy dx. To do that, I need a picture not of the surface, but a picture of the domain of integration. So let's get a picture of the domain of integration. This tells me that x goes from x equals y, which is the diagonal line, to the right, x equals 1. So here's 1. There we go, vertical line like that. And so it's filling in this way from 0 height to 1, to a height of 1. And so, yeah, that's going to be this triangle here. Okay, like that. Can I now think of this as upward arrows? Sure, that should be no problem, right? The bottom of the arrow always starts on this horizontal line. That's y equals 0. So y starts at 0. Goes up to this diagonal line, which of course is y equals x. So I'm integrating y from 0 to x, and then pushing those from 0 till I get to the x coordinate of 1. So 0 to 1. So that is this switched order. And now I see if I can actually calculate that. Well, I mean, I can at least get further than the other one because I can at least do this first integration. Right? This is going to be sine of x squared times y, evaluated from 0 to x. Which means I plug in an x there, so I'm going to get x times sine of x squared, minus plug in 0, so I get 0. And now this is my second shot at this. I still can't integrate sine of x squared. Oh, but look, everything has changed. This is much easier to integrate. This is just a simple u sub. Let u equal x squared, then du is 2x dx, and look, I have x dx. So this is actually trivial to integrate. This was impossible to integrate using the fundamental theorem, right? But actually making the function a little bit complicated, a little bit more complicated, multiplied by x, in this case was my out. In this case, I was able to just have this be a u sub now. And so a 1/2 comes out, integrating from 0 to 1, sine of u, right? Sine of u du. So that's going to be negative cosine of u, which is x squared, evaluated from 0 to 1. Maybe it's been a little while since you've done u sub, but there we have that. So I'm going to get negative 1/2 cosine of 1 squared, right? Minus a minus 1/2 cosine of 0. Well, cosine of 0 is 1, and cosine of 1 radian is not nice. So I'm just going to leave it as cosine of 1. Pro tip, the cosine of 1 is not 0, right? This is the cosine of 1 radian, which is like 53 or 50, I can't remember, 56, 57 degrees, something like that, of 1 radian. So yeah, that's not 0. I don't know what that is. I'd have to type it in my calculator. So I'll just leave it as negative 1/2 cosine of 1. And then cosine of 0 is 1. So this is just plus 1/2. So I end up getting a quantity. There it is. That's the calculation of that iterated integral. Crazy, huh? All right. Any questions with that? There are a couple of other functions that do not have closed form integrals, and that would be the integral of e to the x squared dx. That does not have a closed form integral. And there's several others. But those are the common ones you'll see, at least when they want you to switch the order. Okay. All right. That, I think, does nice work with 14.1. I think we're doing well with that. So let's move on to 14.2. We've now seen that these iterated integrals can be tied with area, but that's not their main goal. That's not their main function. Their main function is to be used in the process of finding double integrals and finding volume. So what I'd like to do is conceptually argue what we should call a double integral. And then after the conceptual stuff, we will then find out that a double integral can be calculated using an iterated integral of a special type. So we're going to, first off, say, what do we mean when I say a double integral? What is that trying to do, right? And then after that, we're going to say, how do I calculate a double integral? And the calculation of a double integral is going to involve an iterated integral, okay? So let's get started. Here is what we want to do, right? I want to find the volume, under a surface. Okay, so suppose I have some surface, z equals f of xy, right? And there might be some sort of volume underneath that, right? So just as to get a visual going here, right? So maybe I have some sort of like, I don't know, something like that, right? And I want to find out the volume, how much three-dimensional space does that take up when I have this surface here. And I want to figure out how much physical space, 3D space, does that chunk in the corner there take up, yeah? Well, to do this, we should probably quickly review how we found area under the curve in Calc 1, right? So a real quick review of finding area under the curve, something you've not thought about probably in a while because you've had the fundamental theorem, right? But before we do that, I want to sort of recall the steps that we did in Calc 1 to find the area under the curve. We started off with a continuous function. And we started with, there's an x value from A and an x value to B, right? And I wanted to find the area under this curve, right? So the first thing we did was to chop this up into pieces. We made what we called a partition. And so we chopped this into pieces. And for our sanity, even though the math doesn't care about this, for our sanity, we will make this an equal width cuts. And we called that width delta x, right? This was some delta x width along, and they were equal, and they chopped the interval from A to B into those number of pieces. Let's call the number of pieces that it chops into n. So I've chopped this up into n pieces, right? So the first step was take your domain, chop it up into pieces, right? Then, from each one of those pieces, find a representative. Now, in Calc 1, that could have been the left endpoint, or the right endpoint, or a midpoint. You just need a single point from each one of these pieces, okay? Why do we need a point? Well, we need to plug in that x value into the function to get some sense of the height of this rectangle that I need to draw. Because to find the area under this curve, what I'm really going to do is just put a whole bunch of rectangles in it and then add up the area of the rectangles. And at least in the beginning, that'll be close to the proper area. It's going to be off a little bit because I'm trying to measure this curved thing with rectangles. So it's going to be off a little bit, but it's going to be decently close, yeah? So if I choose like right endpoints, and then I plug in that right endpoint into the function, I get a height like this. So that's doing all right. That's getting this area here, but it is an overestimation, isn't it? Because this little piece of the rectangle sticks up and over the graph, doesn't it? So on this one rectangle, it's an overestimation for the area. Okay, that's probably fine. So then I draw another rectangle here, get the height there, and that's going to draw the height. Now that one's pretty darn good. Look at that. It's a little bit under, but boy, just barely. Yeah. And then I do this for the rest of these here. Oh, look at this one. This one's under. This one's way under. There's a whole bunch of area I did not pick up. So maybe this excess will balance that out a little bit, hopefully. And so on and so on. Hopefully you remember doing this in Calc 1. Yeah. Right. So what you would do, split up that domain, partition it, take a representative from each. Here I chose right endpoints. Plug those representatives into a function. That gets you a height, right? Then find the area of each rectangle. Well, the area of each rectangle, that's not bad. The area of each rectangle is going to be the height, right, times delta x. Right, that's going to be the area of the rectangle. So this is of one rectangle. Right? And the height is the function value at these certain representatives. So I need to just multiply function values with delta x and then add up those areas, n of them, right, to get an approximation of the area. So the area is going to be approximately equal to the sum from I equals 1 to n rectangles of f of xi delta x. These represent the function heights. These represent the width. Together, this is the area of a single rectangle, and I want to add up the n rectangles that I have, and that area should be close, approximately equal. Then in Calc 1, what you did right away then is saying, well, why do I stop at n rectangles? Why not like more, right? Why just 2 or 4 or 7 rectangles? Why not 700? Why not 1,000,000, right? And ultimately you came up with, why not push n to infinity, right? In other words, squeeze the partition down, 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 down into infinitesimally small strips, right? And you can do that with the concept of a limit. So you learned in Calc 1 that the limit as n goes to infinity of the sum of 1 from 1 to n of this is the area under the curve. And this is what you define the integral from a to b of a function. That's what you literally defined that to mean. It was the sum of function values times delta x, and then push a limit as n goes to infinity. If this number exists, this exists. If f is a positive function, then this number represents the area under the curve. Okay, I want to take the same spirit of this, same idea, and now do this with a 3D surface. So the first thing we did here was partition the domain. In Calc 1, the domain was one-dimensional. In Calc 3, my domain is now two-dimensional. It's like a grid, right? So if I looked at the top view of this, right, I would see something that looked like this, right? So what I want to do is chop this into pieces. So I might do something like this. I'll take the x, this interval, and I'll chop it up into equal pieces like this, equal width pieces. And this will be some delta x. And I'll take this and I'll chop this into some equal width pieces. And we'll call this delta y. So we actually make like this little grid. Right? Okay. So we now have in the domain a grid. And check out one of these cells, like this one right here. See this? What I want to do is use that to represent the function height for this little bitty area. Just like we took one point from an interval to represent the height, right? Here I want to take a single point from each one of these cells, and that will represent, I'll plug that in and get a height. Now, what that's going to do is give me a box, isn't it? I'm going to have this rectangular base, and then when I take a point from that rectangular base and plug it into the function, I'm going to get a height. So that's going to form the volume of a single box. Let me see and bring up a picture here from the textbook that can be quite helpful for this. Give me a second to bring this up. Okay, got it right here. Yeah, so take a look, right? We got this idea here. We have this, and here's the grid I was talking about. Chopped it up into the grid like this. And now I take a representative from each one of those cells. Yeah, they call the one representative xi, yi. Okay. Then plug that into the surface to get a height. See this? Let me zoom way in on this. See this? See how you have this box, and that's representing the volume under that portion of the surface. You can also see that this box sticks out a little bit. So just like my picture on paper, this is an overestimation, isn't it? At least on that little area, at least on that little spot, I'm overestimating the volume, but not by much. Yeah. Okay. Now imagine doing that for every box, for every location here. You pick a point from every one of these grids and you plug it into the function and you draw the box that you get there. Now look at that. That's sort of filling out that space pretty nicely, isn't it? I mean, there's a lot of overages, a lot of overestimations here, right? But then there's nothing here. There's like no box here. So that's really underestimating there and underestimating here. Bottom line, take all of these and I want to add up all these volumes. Sound familiar? I want to add up all of these volumes, and then I'll have a statement that says, well, the adding up of the volume of these boxes is approximately the volume under the surface. Close. Just like we said over here that the sum of the area of the rectangles is close to the literal area under the curve. Yeah? Okay. So, what I want to do there is sort of bring this together and define the concept of what's called a double integral. The name double integral comes from the ability to add up in two ways. Because really what you're doing is you're going to want to go through this grid, right? You can either go start on the bottom here and go left to right, picking your dots, and then you go up to the next row, then you go up to the next row. So that's, that's one sort of addition. I want to add this way. But then once I'm done adding horizontally, I want to add up all of that vertically, right? I want to say, okay, add in these, then add in these, add in all of these, add in all of these. And so there's two sums going on, okay? All right. This brings me to the following definition. Definition of a double integral. Okay. If f is defined on a closed bounded region, okay, called R, in the xy plane, then the double integral of the function f over R is. Here's the notation that we're going to use. So I write two integral signs with an R sort of like in the middle, like that. And so this is just indicating I'm double integrating over a region R. Then I tell you the surface that I'm working with. And then I tell you with respect to what. Since it's with respect to the dimensions of the domain space, we call these capital dA. We call this D capital A. A standing for area, right? Much like in Calc 1, we called it dx, delta x here, right? And that was an interval idea, right? This is just a one-dimensional idea, so we called this delta x. Here we have delta x times delta y. And so this thing forms an area. So you can think of it as saying that dA equals dx, dA here equals delta x times delta y, right? Those two multiplied together like that. All right, but that's just a notation, right? What does this mean? What does this calculate as? we define it to be the following. This is the limit as n goes to infinity of the sum from I equals 1 to n of your representative points, f of xi, yi, those are the heights of the boxes, times the area of the grid in the picture there, right? So you have an area times a height. That's going to be the volume of each box. You add up those n boxes, and then ultimately, to get a better and better and better approximation, you push n to infinity. So you squeeze more and more and more boxes, shrinking, right, the delta x, shrinking the delta y. So you get more and more and more, and it sort of conforms to the shape more and more as you have it. Okay? So we have this double integral idea. So conceptually, that's what we're talking about, right? And we can say the following a statement, just like in Calc 1. If the function is greater than or equal to 0, then the volume under the surface right, over R is the double integral. So if I can calculate this thing, then that's going to provide what the volume is under a certain surface. You give me the surface, I'll plug it into here, and then luckily I don't have to do this. Luckily I won't ever have to use the actual definition, because we're going to tie this to iterated integrals really quickly. And in fact, let's stop there, and I'll start that up next time. So what we're going to end up saying is, to calculate a double integral like this, we can convert that to an iterated integral, which we covered in great detail tonight. Yeah. And so we'll see how that gets connected next time. Yeah. And we'll also be able to calculate the volume of things, and then we'll start to get into what the double integral else can do, just like we did in Calc 1 with the regular integral, right? And then especially in Calc 2 with the applications of that integral. All right, with that being said, hope you're all doing well, taking it easy as best you can, but you do have an exam, so you got to study for that. But anyway, hope to see you next time. Stay healthy, stay well, and until next time, bye now.